get started.
Okay, yeah.
I'll pass it over to you.
Oh, this works well. Okay.
Yep, looks good.
Yeah. Okay. Then I'll start. Thank you for introducing me, and thank you for everyone coming here. And my talk name is Arithmetic Geometry of Parabolic Character Stacks and Varieties. And here is an overview of this talk. At first, I'll give some brief notion of character stacks and variety at first. And then I'll define the E-polynomial, which is a useful tool of this research, and give some properties to say that why this is significant in this research. And then I will define the parabolic character stack and variety, which is major object in this talk. And then I'll give some lemmas and some results of some specific cases. So let's consider algebraic group G, such as GLN, and gamma be a finitely generated group, such as D to the R. And then we can consider the set of all homomorphisms from gamma to G like this. And I will call this set as the home set from gamma to G. Moreover, the group G can act on this home set with conjugation like this. With this home set and group, we can consider some geometric object. At first, the representation variety is just a home set from gamma to G. So this is variety because this is defined over algebraic group G. So the algebraic and geometric properties comes from this G. And the next object is which is called the character stack, which is the quotient of this representation variety. And here, an equivalence relation is just placed by the group action. So this is conjugation. So this is called the character stack. And there is one more geometric object, which is called the character variety. And this is the algebra geometric quotient, or sometimes called GIT quotient, of this representation variety. And here, this variety is two homomorphisms identified when their obic closures intersect. Or if you don't know the GIT quotient verb, you can consider some equivalence relation, which gives a variety rather than the representation variety. As an alternative definition, this is same with the spectrum of prime ideas of ring of invariant like this. So similarly with the representation variety, the algebraic and geometric structure comes from the algebraic group G in this character variety. Moreover, the character variety play a crucial role in diverse areas such as non-abelian Hodge theory, geometry Lagrange correspondence, and mirror symmetry in mathematical physics. So I think that's why many people are interested in such varieties. Before saying my result, let's consider some examples related about this. At first, let's take the finitely generated group gamma G, which is generated by such 2G element, and satisfy this relation. And here G is larger or equal to 1. And then we can take the representation variety from gamma G to R, which is isomorphic to R to the 2G. And in fact, this gamma G is the fundamental group of compact Riemann surface with the genus G. So we will come back this group later. And the next example is given by Fritzsche, Klein, and Roth. We can consider group SL to C and F2 here F2 is the pre-group over rank 2, so finitely generated group. So we can consider the character variety from F2 to S2 to C, and which is isomorphic to C to D3. So this is the, I think, simple example of some representation and character varieties. And my goal of this talk is understand some topology and geometry of certain character stacks and varieties. But this is some elusive problem, but there is a useful term in our case, which is called E-polynomial. Moreover, this E-polynomial is essential for studying some properties, some other varieties, not only for character stacks and character varieties. So I'll define this E-polynomial at first, and in the next slide, I'll give some properties of this E-polynomial. Now, let's consider a complex variety X, then observe that the value conjecture implies the existence of the E-polynomial satisfying the following two properties. The first property is that if X is projective and smooth variety, then each E-polynomial is the Hodge polynomial defined like this. And in this case, this is a refinement of the Poincare polynomial of X. So this is the first property of the E-polynomial. And the second one is that if X is not a projective and smooth variety, and then its E-polynomial is just sum over two polynomials of G and X minus G. And here, G is a closed subvariety of X. So by summing these two E-polynomials, we can get the origin one. In fact, I think this definition is a little bit ambiguous to understand for now. So I just give some properties of this E-polynomial to say that why this is useful. So the first one is that the dimension of variety of X is same as the half of total degree of this E-polynomial. And the next one is the Euler characteristic of X is same as the value of E-polynomial by replacing U and V to 1. And last, the number of connected components of X is same as the leading coefficient of this E-polynomial. So by computing this E-polynomial, we can get at least three properties of variety X. And here are some simple example about checking these properties. Thus, we can consider the projective space P to the N, and then its E-polynomial is computed like this. And then we can see that the dimension of this P to the N is N, which is same as the half of 2N. Here, 2N is the total degree of this E-polynomial. And its Euler characteristic is n plus 1. And we can see that by replacing u times v to 1, this is same with the n plus 1. And the number of connected components is 1, and which is same with the leading coefficient of this E-polynomial. So this is some properties why I use the E-polynomial for on this research, but computing this E-polynomial is very subtle. But here is a theorem which will give a relation between the E-polynomial and the counting polynomial. And this theorem is proved by Katz, and this theorem says that if X is a polynomial count, which means that there exists a polynomial Pxt which satisfying the Pxq is same as the number of points of X over finite field Fq. And if this Pxt satisfies this relation, we can recover the E-polynomial of X by replacing t to the u times v. So the problem of computing the E-polynomial is changed to find the number of points of X over finite field. as an example, we can take the same variety p to the n, and you can easily check that the number of points of x over finite field is same in the q to the n plus 1. And then the Katz theorem says that if we replace q to the u times v, then you can get this result. And you can see that this is same with the previous result in the previous slide. So this is an example of Katz theorem. But sometimes we cannot use Katz theorem because some varieties does not have such counting polynomial. For example, some elliptic curves do not have such counting polynomial. And in that case, we cannot use this theorem. But in this talk, parabolic character stacks and varieties satisfy this theorem, so we will use this theorem for computing the E-polynomial. Now, I will define the parabolic character stacks and variety. And to define such object, we need the fundamental group of K-punctured compact Riemann surface, and its genus is G. I call this fundamental group as gamma G, K, and gamma G, K is presented like this. And note that from gamma to gamma K is derived from the around the circle of each puncture. So there are K more elements than without puncture. And as a simple example, we can find the fundamental group of torus without puncture, which means that G is 1 and K is 0 in the above statement. And that is same with this one, and which is isomorphic to D times G. And this is a visualization of this fundamental group, gamma 1, 0. So with this fundamental group, we can now define the parabolic character stack and variety. Let's consider a fixed tuple of conjugacy classes from C1 to Ck of G, and then the associated parabolic character stack is the quotient of this set. And similarly, the parabolic character variety is the GIT quotient of this set. And you can see that this relation comes from the relation of fundamental group, gamma G, K. And briefly, you can consider this set as some restriction of the representation variety from gamma G, K to group G, because the A1, B1 to AG, BG are go to any element, but from X1 to Xk goes on element in C1 to Ck. So you can consider that this gamma 1 to gamma K go to some element in from C1 to Ck. So that is why I need the fundamental group to define these character stacks and varieties. And people state my result. Here are several other results about the parabolic character varieties using the E-polynomial. At first, Hausel and Rodriguez-Villegas considered this one puncture case, and here zeta is a primitive absolute of unity. And moreover, Hausel and Rodriguez-Villegas literally extended their result by considering multipunctured case like this. And here, they consider the fixed generic semisimple conjugacy classes from C1 to Ck. And I will introduce this definition generic condition later. And in both cases, they found their counting polynomial, so they lastly figure out each E-polynomials. And more recently, Lutillier extended this result by extending just any arbitrary generic tuples, but he considered closures of each conjugacy classes. So as a variety, a little bit different, but main streams are same. And until now, they consider the fundamental group of compact Riemann surface with some punctures, but there are other Cater stacks and varieties whose fundamental group is different. So as an example, Letellier considered the fundamental group of compact non-orientable Riemann surface, and he considered the following two stacks mainly. So also in this paper, he considered the counting polynomial of these two stacks, and this relation just comes from the fundamental group of such non-orientable case. So now our aim is to compute the counting polynomial of parabolic Cater stacks and variety. So here is a theorem which relates the counting polynomial to complex representation theory. This is called Frobenius theorem. And let's consider H be a finite group, and from C1 to Ck are conjugacy classes in H. And then the size of the following set can be expressed as a sum over the set H hat. And here, H hat means that the set of characters of reducible complex representations. More explicitly, the size of this set is same with this summation. So the problem of computing the size is tended to just computing this summation. And you can see that this is very same with the definition of parabolic Cater stacks and variety. So with Katz theorem and Frobenius theorem, you can get such corollary. For a parabolic Cater stack M of GLN, and here G is larger or equal to 1, and CIs are conjugacy classes of XI in GLN, and where XI has a finite order in GLN. And then the counting polynomial of this parabolic Cater stack is same with this. And here, the difference is that there are no sides of G because we take a quotient for defining this stack. So now our problem is computing this sum. But the problem is that if we choose different conjugacy classes, and then we get the different parabolic Cater stacks, that means that we can, this value is dependent on the choice of conjugacy classes. So I'll choose some specific xi's to say more simple result. In this talk, we will consider two punctured case, which means the case 2, and I will choose x1 as a regular semisimple element and x2 as a regular unipotent element. Briefly, the regular semisimple element means that diagonalizable element, and with every eigenvalues are different. Regular unipotent means that unipotent with one Jordan block. Here are some lemmas. I will say why I choose such two elements. At first, for a regular semisimple element x1, each character value is not banished if and only if this character K is the character of some irreducible subconstituent of this principal series. Here B is Borel and T theta is a character of maximal torus T. And the next lemma is that for a regular unipotent element x1, x2, and let's denote from chi-on to chi as the set of irreducible characters of each principal representation series. And then if chi I of x2 is not 0, then for other chi j, for other chi j's, chi j x2 is 0, except j is equal to I. So these two lemma says that for computing the counting polynomial, we don't need to consider every characters of G. The first lemma says that we only need to consider principal series representations, and moreover, X2 says that only specific one reducible subconstituent for each principal series representations. So that is why I choose such two elements. So to reduce some, so remove some characters of G. As an example, here are some character values of x1, x2 in GL2FQ. In fact, in GL2FQ, there are 4 types of characters, and the previous 2 lemma says that the second and fourth cases vanish. So we only need first and third case only. And more explicitly, there are q to the square minus 1 cases in GL2FQ for distinct characters. But if by choosing these 2 elements to compute the counting polynomial, I only need to consider q times q minus 1 over 2 cases. So I only consider nearly half characters of G. So with this assumption, I'll give some result of some special cases. Let's take x1 as some more explicitly. Now, x1 is a diagonal element, a diagonal matrix, and whose diagonal elements are distinct. And this says that x1 is semisimple, and this one is regular. And I'll give one more assumption, such that the product of some AIC is 1, if and only if that is whole product from A1 to AN. And this is called the generic condition of semi-simple element, I said before. And with this assumption, we can get the following theorem. If M is a parabolic character stack with GLN, and let's take a C1, C2 as the conjugacy class of X1, and X2 is a regular unipotent. And then we can get the counting polynomial of M as like this. And here, curly Pn means the set of partitions of N, and P lambda is a parabolic subgroup of Jn, Fq, and alpha lambda is an integer whose value is dependent on the length of each partition lambda. And GGX means the centralized of X. And in fact, we can compute the counting polynomial of M without this generic condition. But if we remove the generic condition, this value is dependent on the choice from A1 to AN. So in that case, I need some more steps for defining this value, for illustrating this value. But by assuming this generic condition, we can get this uniform answer for any A1 to AN. So that is why I assumed the generic condition in this talk. And so we can see that this is by computing this counting polynomial, now we can get some properties of parabolic character stack M. So at first, the dimension of this M is 2g times n to the square minus 2n. And each Euler characteristic is 0. And the number of connected component is 1. So M is connected. This is, we can figure out by computing the leading term of this E-polynomial. And we can check these 3 corollaries with this GL2 case. In GL2 case, the E-polynomial of M is computed like this. And we can check that the dimension is h minus 4 because its total degree is 16g minus a. And each Euler characteristic is 0 because by inserting 1 to this u times v, then this term is vanished, and this term is also vanished. And its leading coefficient 1, so the number of connected components is also 1. So, until now, we see some result of some parabolic character stacks. And in here, we'll consider the parabolic character variety instead of stack. And as far as I know, computing this character formula for character variety is a little bit hard. But we can do that. We can get such very simple result due to generic condition. That is why in previous references, they consider the generic conditions. So in this case, the other conditions are always same. From C1, C2 are conjugacy classes of regular semisimple with generic condition and regular unipotent. So in this case, each counting polynomial is computed like this. The only difference is that here are one more q minus 1 term. So as a corollary, the dimension of this parabolic character stack is 2g times n to the square minus 2n plus 1. And this one comes from this term. And its Euler characteristic is 0 because by replacing q to the 1, and every term vanishes. And we can easily compute that its leading coefficient 1. So in this case, sorry, this is MC. This parabolic character variety is also connected. And both this parabolic character variety and stack cases, we can consider more and more punctures with some unipotent element and regular semisimple element. But in that case, there are more terms appear. So I think this is some base condition of my talk. So I just give these two results with these two punctures. So, and last, here are some references I used from 1 to 4. I introduced in before. And you can see that already other people consider some character varieties in terms of GLN. Here, people considered SLN and SP2N. And I think there are some more character varieties references, but here are some good references, I think. So this is end of my talk, and thank you for listening.
Great, thanks very much. Are there any questions?
I have a question.
Yeah.
Thanks for the talk, Nam. Do you have, and this might be a really difficult question, but do you have any intuition as to why the E-polynomial gives you that information about the topology of the object? So it gives you information about like the dimension and the Euler characteristic and the number of connected components.
Sorry.
So you talked about, you have those three kind of pieces of information that the E-polynomial gives you. Yeah. So the dimension, the Euler characteristic, and the number of connected components. Do you have any intuition as to why the E-polynomial tells you this?
I think that this E-polynomial is defined like this cohomology. So this HPQ means that the cohomology from H0, H1 to decomposition. So I think the highest degree means that its dimension. And sorry, I don't know for all the characteristics, but so its dimension might be means that the number of connected component. And yeah, I don't know the full proof of these three properties. Sorry.
No, that's okay. Thank you.
I think the Euler characteristic is the alternating sum of the Betti numbers, right? So if you sum in
yes.
1, 1 to there, to U and V, you can see that it's going to alternate in some of the Betti
Yes.
numbers.
Yes, right. I think that just comes from definition. Thank you.
Yeah, no worries.
Great. Any other questions? I had one, perhaps another difficult question, sorry, but so the E-polynomial gives you this information, like those 3 properties that you said. Do you know what else it's used for? Like, does it have other sort of things that people use it for, other information that it says? It's okay if you don't know, sorry, it's a tricky question.
Yes, the first time, sorry.
No, that's okay.
Yeah, I want to find some other properties about this E-polynomial, so that I cannot find yet. So if I know later, I'll try to tell you. Sorry.
Sure. No, that's okay. Thanks. Okay, well, if there are no more questions, then let's thank the speaker again.
Thank you, everyone.
Okay, so if people are keen to stick around,